Well, hello, and welcome back to another episode of Quantitative Bites. It's great to see you all. I hope you're doing well. It's been a particularly busy week for me, which unfortunately means I haven't had as much time to work on the spectrogram project as I would have liked to have had. If you remember from the previous episode, I started this as a devlog series, so you could follow me as I create a very simple spectrogram app using C++ and SDL2. And the purpose of this is so that we can take a signal, or so that I can take a signal in the form of a WAV file or the audio track from a video, or possibly from the microphone. We'll see how it goes. And then what I really wanted to do is be able to create animated displays of the spectrogram of that signal, perhaps in real time, though that's not necessarily an objective. We'll just see how it goes. And as I say, this is meant as a devlog series rather than a sort of full-on specific tutorial about how to do this. So I'm really just documenting my progress as I go, and I'm figuring out all the various problems and issues and ways of solving those problems as I go along. So I very much hope this will be of interest to at least some of you out there, and if I can inspire at least some people out there to have a go at building your own small project such as this, maybe something similar to this or maybe something entirely different, then, well, I would be very happy. Anyway, I don't really want to do a very long introduction today. I think we should head over to the computer and have a look at the code that I have been able to put together over the last week. But before we do that, I just want to say, as I always do, that if you like this video, please remember to hit that like button, and if you haven't done so already, please remember to subscribe to my channel so you don't have to miss any future videos. I do try to make a new video every week, typically try to post on Mondays. I don't always achieve that, but if you subscribe, then you don't need to worry about missing anything. Thank you very much. Anyway, okay, I think without much further ado, let's jump to the computer and let's have a look at the code that I've been able to put together over the last week. Okay, so here we are at the computer. The first thing really to have a look at is this is the code that we had from the previous episode. So I won't go over this in any great detail, apart from what I've modified really over the last week. So we have capp.cpp and capp.h and main.cpp. We talked about those. And then we have qblib2d. This is the 2D primitives library. I've talked about that before. There was a separate series on that. I'll put a link to that series in the description below, so you can go and have a look at that. And qbspectlib, of course, is the code specifically for this spectrogram project. So if we have a look in qbspectlib, we created, in the previous episode, we talked about the specplot.cpp and specplot.h files that define the specplot class. That's going to be the class, if you remember, I did show this class structure diagram in the last episode, so feel free to go back and have a look at that if you want. But the specplot class is going to be the class that's actually responsible for rendering the spectrogram into the window. And capp is the class, the main class for the application, and that's going to be responsible for creating the window and controlling the instance of the specplot class. We then have qbspectlib.h, which is a master include file. I think actually I probably didn't talk about that, but it's really a very simple spectlib.h. That's it. It contains nothing really but just two hash include commands. So it has the usual include guards, and then it just hash includes qbdsp.h and spectplot.h, which means that anywhere, if we just hash include qbspectlib anywhere, then we get access to those functions. So that's all pretty straightforward. Now, what I had to make some changes in order to do this. So the first thing that I wanted to do to develop the code from where we were before was actually to change things. If you remember at the previous episode, the code that I created a window and generated a user-defined number of bars, all of fixed height, and they had spaces between them and so on. We took care of all of that. But that's really not very interesting. And of course, we need to be able to set bars of different heights and things. So that was really the first challenge that I had to look at. And the problem that I had was with the rectangle class that I'd created previously as part of qblib2d. Once the rectangle was created, there was actually no way to modify its parameters, which is obviously really no good. The only way of creating then a rectangle of a different height, or a bar of a different height in the context of this specific application, would have been to have deleted that object and rendered a new one, which was terribly inefficient. So one of the first things that I did was in the rectangle class. So I'm looking at the header file here, rectangle.h. So this is from QBlib2D, described in much more detail in the series on the 2D primitives library using SDL and C++. As I say, link in the description below if you want to look that up. So what I had to do was I added a new method to the rectangle class called setPosition, and this allows us to specify the position of the rectangle in terms of left, top, width and height. So notice previously in the previous video, you'll notice I did rectangle, and in the 2D primitives library series I did rectangles in terms of left, bottom, width and height. And I actually, now I started using it more, I realized that doesn't make a lot of sense, because using SDL2, the 0 in the vertical axis is at the top of the window, and the maximum value in terms of the vertical axis corresponds to the bottom of the window. So really it makes a lot more sense to define rectangles in terms of left, top, width and height. So I modified the rectangle class actually to reflect that. Not that that changes anything substantially. Anyway, so setPosition, if you look in rectangle.cpp, and as I say, all of this code I've talked about in the previous series, so you can go and look that up. But this is the new method that I put in, which is the setPosition function. And this really does very much the same as the constructor for the rectangle class. It simply stores the vertices, so it converts the left, top, width and height information into a set of vertices, set of 4 vertices that correspond to the corners. And then, as also described in the previous episode, in I believe episode 6 of the 2D primitives library series, I talked about storing floating point versions of the vertices, and we do that as well. And that's so that we can do rotations. Now, of course, some of you will well be aware that the SDL2 library includes a function for drawing rectangles, and you might therefore really wonder, well, why am I using my own rectangle class to draw rectangles when I could just use SDL draw rect? And the reason for that is because I want to be able to possibly in the future create displays where the rectangles are rotated to arbitrary angles. So the code that I created as part of this 2D primitives library allows me to do that. So it gives a great deal more flexibility than rendering rectangles simply using the function from the SDL2 library. Anyway, so setPosition is really quite basic, just calculates the positions of the vertices and then calls compute bounds and update, and those functions are defined elsewhere. As I say, I didn't really want to talk about that in any great extent in this video today, because it's all covered in the 2D primitives library series anyway. So once we've done that, that gives us the ability to vary the parameters of a rectangle after we've created it. So the next thing that I wanted to do is then to modify the Specplot class. So this is the class that we talked about in the previous video, Specplot.h and Specplot.cpp. And one of the things that I realized previously, I had created mObjectList here. So this stores a list of each of our bars. So each bar is an individual instance of rectangle, and we obviously need to store them so that we can modify them later. So we just store a vector of QBlib2D : rectangle objects, or pointers to rectangle objects. Now, in the previous video, I actually had this as object, and object, of course, is the base class for rectangle. If you look at the class definition for rectangle from the 2D primitives library, it inherits from object, and object is therefore the base class. Now, the reason you might make a list of pointers to base class instances is because then that allows you to create a single array that contains then pointers to any derived class from that base class, which is very powerful. The problem that I found is when I then added a specific method to rectangle, so setPosition here, this is very specific to rectangle, okay? So I also created classes as part of that series to draw circles and filled polygons and triangles. And the setPosition in terms of left, top, width and height isn't going to be the same for all of those. An equivalent setPosition for a circle would simply set the center point, so it would only accept the x and y coordinates of the new center point, so it would necessarily be different. And because of that, I must confess I wasn't really sure how to properly do that as part of the base class. And in fact, I'm reasonably sure that there isn't a really good way to do it. So I had to create this setPosition method specifically for rectangle. And because of that, we can no longer have this as an array of pointers to the base class. We have to actually make it as an array of pointers to the specific rectangle derived class. So that was a change there that I made from the previous episode. The other change that I made was to add a vector of floating point values that we're going to use to store the bar heights. And that's it for the header, what's changed in the header file. So if we go ahead and look at specplot.cpp, we can now see what I've changed there. So in the constructor, just as in the previous episode, we actually initialize and set everything up. So when the user calls the constructor or creates an instance of the Specplot class, they specify how many bins they want, and it's going to equal the number of bars on the screen. And then we calculate based on a bar spacing that for the moment is defined as 2, we calculate what the width of each bar will be and the width of each bin, and therefore the width of each bar, taking into account the spacing. And what I do for the moment is, just to make it a slightly more interesting display, I've put, so we have a simple loop from 0 to num bins, and so for each bin we then create a random value between 0 and 1 corresponding to the height. So simply do, and we store those into m_bar height, which is the vector of floating point values that we just saw. So we push back those, we static cast a float, and we use the rand function modulo 10. It gives random values between 0 and 9. We add 1 to that, so we get values between 1 and 10, and then we divide that by 10, so we get values between 0 and 1, and we store those into m_bar height. And then, exactly as we did in the previous episode, we then go ahead and create the bar objects. We calculate the left, width, height, and top. We simply change the name of that to top, and then we generate the objects using this syntax here. We don't need to change anything here, just because we changed the mObjectList array now to be an array of pointers to rectangle objects instead of pointers to the base class. We don't actually have to change anything, which is really nice. So that stays exactly as it was. And that was really everything that I was able to do on that particular day for this project. So we can have a look. If I go to my terminal window, here we are, and let's just run make. So I went over setting up the make file and everything in the previous episode. Okay, once that's run, if we run the code now, okay, and we get this result. So we see that is somewhat more interesting than the result we had before. So I've also modified the number of bars. So we have 64 bars here instead of just 32. And we can see that each bar is set to a random value between 0 and 1. And we're scaling things so that 0 corresponds to a bar height, a very small bar here, and a height of 1 corresponds to the top of the window. So we can see how that works. And this now gives an illustration of the kind of effect that I want to create with this program. This is with this app. This is exactly what I wanted to do, but I want this to hopefully be animated and to move in response to either real-time data from the microphone. I'm not sure how feasible that's going to be in the sort of time frame I have for this, or at least from data from an audio file such as a .wav file or something like that. So that's ultimately the objective, and I think you can start to see where this is going based on this. Anyway, so that was as much as I got done on the first day that I had a little bit of time for looking at this project. So it wasn't actually until the Friday that I had time to look at this project again. After my breakfast and my normal morning routine of getting some fresh air while I have my morning coffee and check the news, I then set about getting back to work on developing the Spectrogram app. I managed to squeeze in another day of time looking at this project, and I didn't really make any specific changes to any of the actual files or the structure. As we can see, everything here is pretty much as it was before. What I want to talk about, because the focus of my sort of second day of working on this project was very much about trying to display an actual spectrogram. So I want to talk about the qbdsp.cpp and qbdsp.h files that I have in the qbspeclib folder first. And then we're going to have a look at the modifications I made to specplot.cpp. So I implemented the SetData method, which, if you remember back to the first video in this series, the purpose of SetData was so that the user can set the data that they actually want to display, and it will update, then Specplot will update the display of the bars accordingly. The idea, that would be the basis then for creating animation. So let's first of all have a look at qbdsp.h and qbdsp.cpp. So this is the header file. I put this just in a separate namespace, qbdsp, just keeps things tidy. And we have only two functions defined here at the moment. The first one is window Hann. So this creates a Hann window of length n. So I talked about that in the previous episode where I talked about windowing. There's a link in the description below. So go and check that out if you want. I talked a bit about why I'm using the Hann window and a little bit about why windowing is so important when we do this kind of work with the discrete Fourier transform. The other function is DFT. Now I talked about that in a different previous episode when I talked about the discrete Fourier transform, and I gave a brief overview to how the DFT works with code in C++. Again, as before, link in the description below. Go and check that video out if you haven't done so already, if that sounds interesting. So this is exactly the function that we wrote in that from that previous video to implement the discrete Fourier transform, which accepts as input a vector of complex doubles called x and returns an output as similarly as a vector of complex doubles. So if we look in qbdsp.cpp, we can see the code for those. So this is the code that I have for generating a Hann window. It's really very simple. It simply accepts the length of the window as an integer n, so the number of samples that we want. We simply then create a vector of complex doubles called output that we're going to use to store the output. And we then statically cast the number of n to a double because we're going to calculate all of the window values as doubles. They're obviously floating point. So we create a static cast version of n, which we call nd. We then loop small n from 0 to big N, and we also statically cast each value of n. So those are integers. They actually probably could have done those as floats, but anyway, the way I did it was to statically cast each one of those then to double. And then we simply calculate the real part. It is just a real function, but everything I've done using the DFT has worked using vectors of complex doubles. So I've just stuck to using those everywhere because then that's quite easy. So we just simply implement the window, the Hann window this way. Again, if you want to see exactly where that comes from, go back and check out my video on windowing, as I said before, link in the description below. And so we simply use that for equation. We calculate that for every value of small n, and we push those back into the output variable, and then that gives us our window function. It's as simple as that. And the DFT function that I have here, this is exactly the code that we used as part of my the video I did on introducing the discrete Fourier transform, where I just explained briefly how it works and gave this example code here in C++ to illustrate that. Now, of course, this is not the most efficient way of implementing a discrete Fourier transform. It was really intended more for illustrative purposes to show how the DFT actually works rather than being the most efficient implementation. However, it will do for the purpose of the application that we're putting together at the moment. Now, obviously, if you really wanted to do this quickly, you would want to use an implementation of the fast Fourier transform algorithm, which is a lot faster. There are plenty of examples of that out there. If you just Google for it, you can find implementations of the FFT algorithm in pretty much any language that you wish. So I didn't really want to talk about that too much myself. But for now, I'm just sticking to using this code here because that's what we put together in one of the previous videos, and it does the job. It's not the most efficient, but it will get the job done. Okay, so that's qbdsp.h and qbdsp.cpp. So in order to actually display real data, I've made some changes to the Specplot class itself, specplot.h and specplot.cpp. And so we're using, first off, we have our SetData method. So this is as I said at the beginning, this is the method that the user is going to call every time they want to update the data that's going to be displayed in the bar graph. And this actually now accepts simply a vector of complex doubles and data. So even if our signal is actually real, which it will be, we're going to do it in this format because that's simply convenient. And what else did I change? The other changes that I made at this specific session working on this project was I also added here one final private variable, another vector of complex doubles called m_signal window. When the user creates an instance of the Specplot class, they specify the number of bins, and that specifies the number of samples that we're going to be taking in our DFT. We'll talk about that in a moment. And that fixes the length of the window. So once an instance of this class has been created, the length of the window is fixed, which means that we can pre-calculate the window function at the point that the Specplot class is created, and then we simply need to just use it every time. We don't need to actually bother about re-evaluating it each time. Anyway, let's have a look at Specplot.cpp, and we can see what's going on here. So in the constructor, things are exactly as they were before, except that we now generate our signal window. So we call QBDSP : window Hann, and we pass to it mDFT length. I should just talk about that actually. So we calculate DFT length as being the number of bins multiplied by 2. So number of bins is this variable here that the user specifies when they create an instance of the Specplot class. So we're only going to display the first half of the DFT. And actually this has to do with the fact that the discrete Fourier transform has both negative and positive frequency components. It actually doesn't have negative frequencies, it's more of a convention, but it's something I don't really want to talk about too much at this stage anyway. So we define the DFT length as being double the number of bins, and then we calculate our window function, and simply using the function that we just talked about now from the QBDSP library. And then this is all the same, and we create the bar objects and everything exactly as we did before. And actually for now, initially we define them with the same random heights that we used in the previous day's work. So really the big change that I've made is the SetData method, which is here. So this is the method that really does all of the work. So this accepts a signal in the format of a vector of complex doubles, and it then calculates the power spectrum for that signal by applying the window function, and then normalizes those values to be in the correct range, and then generates the actual data that we're going to use to update the bars. So let's just have a look at how we go through and do that. The first thing to note is that we define the input here as const, so that we don't accidentally modify it. And because of that, because we are actually going to modify it, the first thing that I did was then create a copy of that. So simply use this very simple syntax here to copy data into a new variable called temp data, which are of course of the same type. And then it's possible that the supplied vector is going to be longer than the DFT length, or possibly shorter. So if it's longer than the DFT length, then we want to truncate it, and if it's shorter, then we want to zero pad it. And we can do that very easily actually using the resize method from the vector class from the standard library. So we simply check if the size of temp data is not equal to the DFT length, then we do temp data.resize, and we're resizing to mDFT length. And if we need to fill out any new values, that will, if you just did that, then that would truncate as necessary, but it wouldn't know what to do if it had to add new values. So then we pass the resize method the value that we want to use in the event that it has to add new values, and that's simply going to be, they're going to simply be complex doubles with 0 for both the real and the imaginary parts. So that takes care of the situation where our supplied data might be different length to the DFT length. However, my intention when using this function is very much that I will keep those the same. We then apply the window function to the data. That's really easy. That's just a matter of looping through every sample in the temp data vector and multiplying it by the equivalent sample in the mSignal window vector. So nothing complicated there. And we then compute the DFT of temp data using QBDSP : DFT. Okay, so that's from QBDSP.cpp. And that, of course, gives us a vector of complex doubles as we had before. And now we're actually going to compute the power spectrum. So I talked about power spectra in the video on windowing, but I didn't specifically go over too much about how they're actually calculated. So the first thing that we do, we're going to take the absolute values of the DFT, and these are no longer complex numbers. So we simply create a vector of doubles, and we loop through every sample in DFT result. Remember, that's the output of the DFT function here. And we push back into abs DFT the floating point absolute version of that complex number. So that will give us a real number that represents the absolute value of current sample. Remember, current sample is, of course, a complex number, so we take the absolute of a complex number. It gives us the magnitude, which is, of course, real, and we store those real values into abs DFT that we defined just here. We then need to calculate the maximum value of the power spectrum because we're going to need to normalize it, and we do that using the max element method from the standard library using this syntax here from absdft.begin to absdft.end, and that gives us the maximum value. And then we use that to actually normalize. So we simply loop through every sample in absdft, and for every sample we simply divide it by max value using this syntax here. So that then gives us the normalized absolute values, which is very nearly a power spectrum. The last thing that we need to do is take the log of that, and then we need to do a little bit of shifting. So what we do here, this does 3 separate things in one loop here, just to save the number of different loops I'm using. So we convert to dBs. We do that using 10 times log to the base 10 of absdft. We do that for every sample. Now we limit it also to only the first half of the DFT result. Now remember, we define DFT length as being double the number of bins, and this is why. So we're only interested in the first half of the DFT result, and that happens here. So we loop I from 0 to absdft.size divided by 2. And we also limit the minimum value to minus 30 dBs. Now that's the level of the first side lobes of the Hann window. If you go back and look at the video I did on windowing, again, link in the description below, I talk about the side lobe levels and things for the Hann window, and you can see where that value of minus 30 dBs comes from. And we say very simply, we're going to basically clip to that. So if temp value is less than minus 30, then we push back a value to 0.01. Bearing in mind, actually, that absdft will now contain values that are between 0 and minus some arbitrary number, probably quite a lot larger than minus 30, as a result of the normalization that we did here. Okay, so what we're doing now, we want 0 will be equivalent to the top of the screen, and then minus 30 to be the bottom of the screen. And if you remember, the way we configured our bars was that they range between 0 and 1. So we want to change that. So minus 30 will give a value of 0, and a value of 0 will give a value of 1. So that's the purpose of this code here. So if temp value is less than minus 30, then we push back a value of 0.01. Otherwise, we take temp value and we add 30 to it. So then that will give a value that ranges between 0 and 30. And then we simply divide that by 30 then to get a value that varies between 0 and 1. And once we've done that, that is actually the data that we want to plot. So then we modify our m-bar height variable with the values of power spectrum. The reason I've done that in a separate loop there is because there might be additional code. Ultimately, I'm thinking it might be possible to do this using a different number of bars to the number of bins for the DFT. And in that case, then there might be some averaging between DFT samples to calculate each bar height. So yeah, and then we call the update bars function to actually implement that. So I just want to look at update bars because I don't think that was here before. So update bars, this simply loops through every bin that we have and calculates the left, width, height and top of each bar, and then uses the new set position method that we've just talked about to modify each of the bars accordingly. But that's actually it. So the last thing just to look at then is in capp.cpp, because it was necessary to create an interesting test signal, obviously, to display this. So I created a signal with 128 samples in n equals 128 as a signal k of 16. So I'm using k. This is exactly the same as the examples that I used in the video on the discrete Fourier transform. So if you want to know a bit more where that comes from, you can check out that video. And we define a signal, obviously, as a vector of complex doubles. We loop through every sample, so x from 0 to big N, and then we calculate each sample individually, so autocurrent samples, STD complex double, and this is the function I put together. So this is actually a compilation of 4 cosine waves together. So the first one being at signal k, then signal k times 1.5, signal k times 2, and signal k times 3. So those will give 4 cosine waves at different frequencies, and you see they have different amplitudes. First one of amplitude 1, then a quarter, then an eighth, and so on. And we just add those up. So that will create one signal that contains 4 separate cosine components. Now that's an interesting test because it means that when we actually look at the power spectrum for that, what we should get is 4 distinct peaks. And then we simply use the SetData method on mSpecplot to pass that signal into the mSpecplot, which will then cause mSpecplot to go and generate the power spectrum with the code that we've just been looking at. So interesting to note, this is what I was mentioning about at the moment the number of bars that you specify should match the number of samples in the signal. So we have 64 bars, which means we're taking 128 samples of our signal. For now, that relationship is fixed. If you wanted 32 bars, you would have just n equals 64 here, and so on. But for the moment, I think that's perfectly adequate. Nothing else there really has changed. So if I go to the terminal window, where is it? Go to my terminal window. Let's just clear that. So let's just go back into this folder. Let's run our make file just to compile everything. Okay, and run our code. And there we go. Let's switch that over to here so you can see it. And there we are. So we have, that is the result that we're talking about. Can I get all of that on the screen at the same time? Yeah, there we go, roughly. Yes, so what we see is that we have bar heights of 0 everywhere except for the 4 peaks corresponding to the 4 components of our cosine signal. So you'll see that the third one occurs at the halfway point. So if we just look at the code to generate the signal, so that's a frequency of signal k times 2, which of course would be 32. Okay, so signal k was defined as 16, so signal k times 2 is 32, and 32 is of course half of 64, which is 64 is the number of bins. So we see the third one occurs exactly in the center, and you can see how the relative positions of the other peaks here are then defined. We get what appear to be side lobes here, but those come, of course, from simply as a consequence of the width of the Hann window that we've used. It's a very short, just 128 samples, which is really very short. So we do get quite a wide peak. But we can see that really is beginning now to look like the kind of result that we want. So we put a real signal into it, and with 4 cosine components, and we get 4 peaks corresponding to the frequency content of that test signal. And this is really starting now to look like what the final application should be. As I said at the beginning, that is pretty much everything that I had time to do really over the last week. It's not as much as I was hoping to achieve, but what I want to go on to look at now next really is sort of hopefully bringing in real signals, and then we'll be able to look at some spectrograms of real signals, and then hopefully move on to how we might actually go on then to animate that display. Okay, so there we go. That's really everything that I wanted to talk about this week. I really hope you've enjoyed this video. It's been a great deal of pleasure making it. If you have liked it, please remember to hit that like button. And if you haven't done so already, please remember to subscribe to my channel so that you don't have to miss any future videos. Anyway, as I say, it's been a pleasure, and I really look forward to seeing you in the next video. Thank you very much for watching. Bye.